All right. Hey, kids. So this is lecture one of what may be several of me just sitting here flipping through a note packet. I want your feedback on how you like it. What I was thinking is we would at least start with finishing up the one that we've been doing. So if we go back in time, remember we were started with the integumentary system and hair and all of these different glands. This was a long time ago though, and we have the epidermis being that top layer of the skin, then the dermis, and then the hypodermis. And when we left off, remember we were talking about these fingerprint patterns. All right, all of the different fingerprint patterns that developed when we were in utero, in our mother's uterus, developing, and our skin grew quicker than our body did. And so when our skin, our epidermis here, or our dermis rather, grows quick, it folds up, and that's what gives us these fingerprints, these ridges and grooves. And so in our note packet, we really don't have a lot left to go. We really only have to do fibers yet. We never got a chance to do this cyanoacrylate chamber, and we never got a chance to do the iodine, which is something we were going to do when we were out of school on that Friday. So what I was hoping is for us to take where we pick up where we left off. I'm going to record these because our class is going to be meeting, I think, from 9 o'clock to 10 o'clock in the morning, which is a bit of a crazy time for me. So with me trying to homeschool my 3 kids, I was hoping I could use a quiet time to record and do these videos with you. And I should just stop talking and get it done so we can have a nice short video. Hang on one sec, I gotta grab something. So where we left off was fibers. And really there's 3 types of fibers that I want you to be aware of. There's natural fibers, and these are fibers that are derived from plants. Okay, so they're fibers that are derived from plants. Now, if I were to back up just a bit, this is anything that has a long, thin filament. This would be something that our clothes are woven into. This could be something that spins off of a spider or a silkworm. This could be something like wool that comes off of a sheep. This could be a fiber like hemp that comes from the marijuana plant. This could be lots of different fibers. And they are able to be used forensically to leave behind little pieces that can then be matched to the fiber. So we could identify, for example, a carpet or a sweater color or some sort of rope that was used to commit a crime. So that's where we're heading. So these natural fibers, these are plant fibers, and you probably are familiar with, well, you're probably wearing one made of cotton. That's one of them. So those are what most of our clothes are composed of, is this cotton. We are writing on another fiber, which is our wood fiber, like any paper, anything that we use here. And like I mentioned, hemp, which is something that's very common for ropes. These are all considered plant fibers, and they're made of cellulose, which is a polysaccharide. If you go back into your memories, a polysaccharide would be something that is composed of many repeating units of a carbohydrate. So it is many sugars hooked together complexly into a cellulose fiber. The natural fibers could also be protein-based, and they could be animals, coming from animals like wool. They could come from insects, like, for example, silk, or they could be inorganic, but still natural, something like fiberglass, still a natural product, or asbestos. Those are 2 inorganic but still natural fibers. So fiberglass would actually be what your insulation is often made of in your house, and it's long, thin pieces of glass, of a glass-like material. So it would be silicon and oxygen hooked together. So that would make it natural, but inorganic. It didn't come from any plants or animals. All right, and if you drop down on your note packet, you're going to find that we have these natural protein fibers We've got natural protein fibers in this column. This incorporates the wool, the silk, the angora from a rabbit, the alpaca from alpaca. This is from sheep, some sort of a protein fiber like the animal fibers that we just mentioned up here on this side, right up here. So these would be the protein. I never wrote that down. So these top two would be made of proteins. And it just talks to you a little bit about them. They have good tenacity, means they stretch really well without breaking. We do an activity in our lab where we actually would have burned this natural protein fiber, and when you take a little piece of yarn, it actually shrinks and burns, so it just shrinks right down into almost nothing. You guys probably have a fairly good idea of burning fibers, because if you've ever burned something synthetic like nylon or polyester, you've probably done this if you've strung a lacrosse stick, or if you've had the cord, like the paracord, if you've ever done any work with that, and it melts right at the end. And so we've used that before. Well, what we would have done is we actually would have burned each of these different fibers. And their burning helps us to identify the fiber, what it smells like, how it burns, does it melt, does it burn, does it flame up. We also in our lab would have we would have dropped them in a little bit of hydrochloric acid, a little bit of bleach, and we would have checked its reaction to alkalines or acids. So that would have been cool. But seeing that we're home, we aren't able to go ahead and do all that, so we're just going to talk about what would happen. Our natural cellulose fibers are the other ones that would be up top. Okay, these would be our plant fibers. These would be our flax, our cotton, our jute, and our linen. These are all of the things that we make our clothes, a lot of the ones that we make our clothes out of. They are cheap. They're easy to make. They burn pretty easily. They do stain with an acid and sort of melt in an acid. They just sort of respond like we would be familiar with. And this would be like the t-shirt that you're wearing. Paper obviously would burn. A hemp rope, we could burn the end of that. It wouldn't melt, it would actually burn. It would flame up. So these would be the fibers that you're probably most familiar with because they are common everyday fibers. The regenerated fibers, these would actually just be a processed natural fiber. A processed natural fiber. This would be something like rayon. So rayon would be that silky blouse or silky dress that you wear for nice occasions. And this would actually be cellulose from trees. Cellulose is the material that makes up the cell walls of plants. So cellulose from trees, that is then chemically altered. By CS2, and then it's shaped. So carbon and sulfur, and then it's shaped. And it's shaped into that rayon material. It would be dyed then at that point. Acetate is another one. And acetate would actually be soybean fibers or corn, soy, peanut, or milk fibers. Milk has a material called casein in it. And so if you were to take milk and you could actually make like a rubbery plastic material out of milk. You could take this milk and you could add an acid to it, and it would pull out that casein and make it very pliable. So you could take something that we drink with dinner and make it almost into plastic, and then you could harden it and it would be very hard. So what that is actually taking a fiber, a natural fiber, like like soybean fiber, corn, soy, peanut, something that you have in your house, and altering it with an acid and making it into a material like acetate. All right. Synthetic fibers, these are not natural. That's why they're called synthetic, right? So you're like, duh. So not natural material. And these would be the strongest of all known materials. So these would be the strongest of all known materials, or all known fibers. Usually they're pretty elastic. I hope I'm on my... Hope we got it all. I'm going to just zoom out just a smidge. I'm not high tech here. So elastic means they could be stretched. Usually these synthetics are also thermoplastic. What is thermoplastic? Plastic means it can be molded. So thermoplastic would just mean that it can be heated and then molded. Heated and molded. All right, and these are the synthetic fibers over here, the ones that I had mentioned, like your paracord, which melts. These have a good rigidity. They're able to be pulled and yanked on and not rip or tear very easily at all. They can withstand pretty high temperatures. They're pretty resistant. And so we do a lot with these synthetic fibers. We make a lot of stuff with these synthetic fibers. And the materials that I'm talking about, these would be things like nylon, polyethylene, acrylic, and then PVC. PVC would be the piping, that white piping that probably makes up the drains of your sinks, stuff like that. It's very rigid, very, very resistant to any wear or tear. All right. A few things that you need to know that you need to make sure you mention right down here on the charts. For this one, the natural proteins, since it's a protein, the building blocks for this one are amino acids. And you need to remember that. So the amino acids make up the proteins. The building blocks for these two over here, these cellulose, the building blocks would be a simple sugar. Because remember I said they were polysaccharides, which means many sugars hooked together. So the building block that makes them up, is simple sugar. Simple sugar. All right. Just a few other things where it talks about tenacity. Tenacity here just means that the fibers cling and are not pulled easily apart. Fibers cling and are not easily pulled apart. So everything else you can probably read yourself. It's pretty clear what some are affected by acids, some are burning like paper, some smell like hair when they burn, like those protein fibers. All of them are pretty straightforward. But again, tenacity just means the fibers cling together and they're not easily pull apart. So for example, something like rayon, the viscose, these actually, if you cut them, they would fray and they would sort of pull apart. Whereas if you cut a cotton t-shirt, the end of it would just sort of wrap around. So if you've ever altered any of your clothes or cut them on accident or on purpose, these rayon materials, they would just fall apart. The weave would just sort of fall apart. So that's the tenacity. All right. If we continue on, I just want to go through one last thing. So the forensic application for these fibers, and again, we're pretty close to being done with our notes for today because I'm going to stop at fibers. What is the composition of a fiber? All right, so what you need to know is what is the monomer? Mono means single, so monomer would be the unit, the simple unit that makes it up. So is it made of amino acids? Is it a protein? Or is it made of simple sugars? Is it a polysaccharide? What is the unit that makes up all of these materials? So that's the first thing that needs to be determined is what is the composition of the fiber? Is it a protein? Is it a cellulose? What is it made of? Some other physical properties that you could do that you're probably catching on to. Let me just make sure we're on the screen because this is probably really annoying if I'm not. All right, so what is the melting point? What's the melting point? What's the refractive index? What's the chain length? How many of these monomers are hooked together? That's something that can be determined. And then what's the opacity? What's the amount of light that passes through it? So those are things that would need to be determined as far as the physical properties. They would be properties that would be able to be determined forensically to figure out what type of fiber it is. As far as the morphology, probably the last time you have seen this word morphology was probably in biology class, and morphology would be what's the visual appearance of it. So in the last time you would have done it would be the morphology of a plant when you talked about leaf structure and veining of a plant. It was actually in one of those New York State labs you did eons ago. So what is the shape of the fiber? So what's the fiber shape? Cotton would actually have fibers that are shaped like this. Rayon would have little beads of material hooked together. That would be the fiber shape. Wool's like little snarls, sort of like little curlicues. That would be the fiber shape for that one. And then nylon looks like little plus signs. So you could actually look at these fibers and each of them have their own distinct shape. All right, is the fiber part of a larger piece of evidence? So is it cloth? What's its pattern of weave? And I gave you guys some readings that talk a lot about weave. What's its color? Is it a textile? Was it made in some factory somewhere? Is it yarn? If so, is it wool? Is it twisted? And if we were in class, I would probably give you a piece of yarn and I would actually have you do an activity with that yarn where I'd have you unravel it and look at all of the different variations and just the twisting of some yarn. It's ridiculous when you actually look at a piece of yarn. I could give every one of you a different piece of it and it would all be twisted and woven a different way. So that's pretty awesome. Is it from a carpet? Like the list can go on and on. What is the composition of these fibers? So not only are we talking about how the fiber reacts to something like flame, does it melt? Does it melt in acid? What's its simple composition? What's its monomer that makes it up? What's the fiber shape? But then the overall pattern of the bigger piece of that fiber. And then are there any cut marks on this fiber? Are there any striations on the fiber? And we can keep on going. And if you notice right here, we have a little bit on weave. This, again, like I said, is in our reading where it talks a little bit about all of the different weaves that we can use for our fibers. That can be an identifying characteristic for forensic application also. So let's just go ahead and read down here. This is the Jeffrey McDonald case, and this was way back from 1970. I'll actually let you read this on your own, but I would like you to read this case down here at the bottom because this is an excerpt from your textbook about fiber evidence used in the solution of a crime. All right, if you can hang in there, I think I'm just going to keep on going. I had intended on just doing fibers this week, but seeing that we're so close to being done, I would like to do a little bit on biometrics. I do need to grab one thing. Hold on. Sorry about that. All right. So we'll switch colors. So Alphonse Bertillon You guys probably remembered him from Unit 1 way back at the beginning of the year. Do you remember? He was able to do the identification of people based on simple measurements of their body parts and other features. Do you remember how he had that Bertillon? And we did a lab where we talked about people's measurements, and we put their measurements up on an index card, and we tried to match their measurements. And this was a method of anthropometry, identifying that person based on their measurements. And so biometrics sort of takes this, but takes it a little bit further. So this is basically the application, biometrics, the application of, statistical methods to biological data. So it's a far jump from Alphonse Bertillon and the mugshot and all that went into that. And it's the idea that one trait can identify one person from all others. So the 3 steps of, this is supposed to be of, I never noticed that before. The 3 steps of biometrics. Sorry, let's see if I can get, my phone is literally balanced on a water bottle, so it's really not ideal. But we're going to make it work, especially for today. All right, so the 3 steps of biometric would be enrollment. This is just the registration of information. So we need to gather the information in order to get it into a system. So for example, this would be scanning a fingerprint into a database. All right, and then we need to do the storage of this biometrics, which would be something like the characteristic retention. And this would be digitally recorded. And then we would do comparison. So this would be the method of looking the information up, for each individual. And the speed depends on simplicity. So when I talk about biometrics, I'm talking about lots of different things. We're talking about fingerprints, palm prints, DNA, hand and finger geometry, writing and typing analysis, vein geometry, like looking actually at the pattern of somebody's veins, eye biometrics, voice analysis, face image data, ear canal biometrics, like some things that we've never thought of before. Odor prints, just somebody's odor that they give off. And I don't mean that in a bad way. Everyone gives off their own odor. And sometimes if you have a more sensitive nose, you can actually smell somebody as they enter the room. They actually smell different. Lip patterns, palate ridges. Palate would be the top of your mouth. We all have a distinct pattern on our palate. So maybe we'll get a chance, I hope we'll get a chance to do some of these biometrics. Maybe some handwriting analysis is pretty fun. So maybe we can just look at handwriting. The JonBenet Ramsey case is a perfect example because handwriting analysis was used in a huge way for that case. So maybe we can look back at that again. So that is where we're heading. I don't know, this part doesn't really work too far into the class because we're not using all of this. The reason is we actually don't have all of this information registered. So if you've ever thought, none of us have had our ear canal biometrics taken. Nobody knows what our ear canals look like. So we don't have the enrollment of the information. So this isn't something that's used tons, but here's a little bit on voice analysis and different ear acoustics from different people. So that's pretty cool. And here's an iris scan, just scanning the iris. So a scan to see an entrance into a top secret place. We could scan our eyes with our iris scan. So we all have a distinct characteristic there in our eyes. So maybe in your lifetime, you'll see this biometrics sort of explode. Right now, we're not huge into it. We're using mostly DNA, mostly fingerprinting, a little bit of handwriting analysis, a little bit of voice analysis, a little bit of iris scanning, but that's about it. So maybe this will take off. Maybe one of you guys will be the pioneers in the biometrics field. That would be awesome. So that's all the notes I think I'm going to do today. That actually finishes our note packet. I would love a little bit of feedback on how I can help you guys with getting all of this stuff done. What I've done is I wanted to do this week all of our fibers. So I gave you two readings, one on Kevlar and one just sort of a general fiber reading with some questions. And I wanted you to use Kami, whatever that's called, to edit that and just to put text boxes in it or just write on it and then submit it that way. So hopefully this gives you enough information to be able to finish our note packet, and then you can do those two readings, and that will be all that we're going to do on fibers for this week. One more last little tidbit while I have you guys listening to me. You should have listened to the toxicology lectures. That is an assignment that I do want you to complete. So I would like you to listen to those lectures and learn a little bit about toxicology, and then I'll give you some follow-up assignments probably next week on that. So let me know, give me feedback on what's working, what's not, if you like this rather than the lectures, or if you want to go back to the lectures given by the professor up at Syracuse. So please go ahead and let me know what's working and what's not and what I can help you with. And I will be in touch as far as class and office hours and how you can get in touch with me. Thanks so much. Talk to you later. Bye-bye.